When the Andromeda and Milky Way galaxies collide, will their black holes merge or will they remain as two separate entities? And what does actually happen when two black holes meet?
So the first answer is, I don't think we know when the Milky Way and Andromeda collide whether the black holes will merge. I mean, we certainly know there's an interaction between the galaxies. We know the galaxies will merge. So my guess, not actually knowing the latest research, is they probably would eventually, I think. But it depends on the angle that they hit each other and so on and so on. And also the timescales. I mean, it may be that they'll inevitably merge in trillions of years, but not billions. I don't know. But we do know what happens when black holes collide because we've observed it. So our latest detectors, which detect so-called gravitational wave detectors, which detect unbelievably ripples in the fabric of the universe, ripples in space and time from the collision of objects like black holes, are now working beautifully. And we've seen several occurrences in the universe where black holes have collided with each other and merged. And so what we know is that they form a black hole. They lose some energy when they collide, but they do form a black hole with an area, a surface area which is bigger than the two holes that collide. And that was a prediction from Stephen Hawking, the so-called area theorem. And that's been proved. So, and the prediction of how they collide and how they merge and what you get afterwards is in absolute accord with Einstein's theory of general relativity, which was published over 100 years ago. And Einstein didn't know that there were such things as black holes when he published the theory. He certainly didn't know that we'd ever see them collide together. He certainly didn't know that there were ripples in the fabric of the cosmos, although he predicted that slightly later, that would carry the information, just like light carries the information from distant stars, so the ripples in the universe can carry information from collisions of black holes. So in the last couple of years, we've entered a new age of astronomy where we can watch black holes collide. To reverse Stephen Hawking's area theorem, which seems to have been proved by these collisions now, says that if you collide two black holes together, then the area of the horizon around the new black hole has got to be bigger than the area of the horizons of the two little black holes. And that seems to be what we've seen. What is that thing, the event horizon? It's the area around the black hole from which light can't escape. So if you go into a black hole, which you could do if it's sufficiently big or sufficiently massive, you could fall in through this point, this sort of region of space around the hole, and you could easily fall in. And what would happen when you fall in is that you could never get out again, and you couldn't even send a signal of light out of the black hole because the gravity is so strong that the light can't escape. And the region from which the light can't escape is called the event horizon, or inside this event horizon. And that's what you see with the black hole. If you could float around and see one, you wouldn't see anything because it would be black, but you would see this sphere or this shape in space from which no light would emerge, and around which all the light from the distant stars and the galaxies would bend and curve and be warped. So that's a very strange thing, a black hole.
Curious about what's in the black hole, the singularity. Is it a highway to another dimension, or are there different universes inside?
First of all, what happens in there? By the way, the supermassive ones at the hearts of galaxies, we don't really know how they form. It's one of the things that the Square Kilometre Array, mainly north of Perth here in Australia, is going to look at the formation of the first stars and galaxies to try to understand how those enormous things, many millions of times the mass of the sun, get into the centre of galaxies. But the smaller ones, the little ones, let's say the ones we've seen collide, which are about 30 times the mass of the sun, the big ones we've seen to collide, those form by the collapse of massive stars. So what happens is a star is holding itself up against the pull of its own gravity, which is trying to squash it down because of the nuclear reactions in the core of the star. So because the star shines, and that produces a pressure, if you like, that holds the thing up. But it can't keep burning its fuel forever, and when it runs out, gravity will take over again. And in the case of the most massive stars, then no known physical process can stop the collapse. So gravity wins. So it just collapses and collapses and collapses. As far as we know, forever. So you get an infinitely dense point of what, I can't even call it matter. It's gone, really. All there is left is the gravity, in some sense. Now, we don't know whether that's true, because we don't know the physics. When these things get so dense and so tiny, we don't know what the physics is. So it may well not be just this infinitely dense point. We just don't know. But so we give it a name, the singularity. But all that's left that you can observe in the universe is the gravity. All the matter is kind of gone into this. So it's one of the great questions in physics, and it's very strange that strange things happen. For example, we can work out what the circumference of a black hole is. So we can go round the event horizon and say, well, it's so big. But if you say, what's the distance from the event horizon to the centre, it can be infinitely big, as far as we can tell. So it's like a TARDIS, in some sense, inside a black hole. So we just don't really know. But it can be a lot, the radius can be a lot bigger than the circumference would suggest, because of the curvature and bending of space and time. So they're really weird, basically.
Since gravity pulls things into a black hole, why can't light, which has no mass, escape?
Oh, so you're kind of correctly thinking about gravity in terms of the way Newton described it, which is that it's a force between massive objects. But in Einstein's theory, which is better than Newton's, it isn't that. What it is really is so if you imagine the universe, really you can imagine space and time as sort of a fabric. It's often called the fabric of the universe. And the sort of picture that many people use, which is quite a good picture, if you imagine putting something like a bowling ball or a cannonball in the fabric, then it curves it. And so you can imagine this sort of curved sort of well in the fabric, which goes down to where the heavy thing, the massive thing is. And if you imagine rolling a marble or something around there, then it's not going to go in a straight line, it's going to bend around. And that's the same for light as well. The light waves, or the particles of light, if you like, called photons, follow the path through the curved space in the same way that massive objects follow the path through the curved space. So Einstein's theory naturally predicts that light is bent in the same way, that the path of light is bent in the same way as the path of anything else through the curved space.